An internet cable can detect an earthquake without carrying a single phone call. That sounds impossible. A fiber optic cable is supposed to move data as light. So how can it also notice the ground shaking? The strange answer is this. The cable does not need tiny microphones along its length. The cable itself becomes the sensor. Inside a fiber optic cable is a hair-thin strand of glass. Light races through that glass, carrying messages across cities, oceans, and countries. But the glass is not perfectly smooth. It has countless tiny imperfections. Each one sends an extremely small bit of light back toward where it came from. Normally, those faint returns form a steady fingerprint of the cable. Now imagine the ground moves. An earthquake sends waves through rock and soil. The cable bends, stretches, and squeezes by tiny amounts. Too tiny for your eyes, but not too tiny for light. When one section of glass stretches, the returning light from that spot changes slightly. It arrives a little differently than before. A machine at one end of the cable sends quick pulses of laser light inside. Then it listens for those faint, returning signals. Not with ears, of course. It measures light. If the ground shakes near kilometer 12, the fingerprint changes near kilometer 12. If the shaking moves down the route, the changing pattern moves too. So one long cable can act like thousands of closely spaced motion sensors. This method has a name: distributed acoustic sensing. Distributed means the sensing happens all along the cable. Acoustic means it can notice vibrations, including earthquake waves. Here is the clever part. Scientists do not have to dig up a road and install thousands of separate instruments. The glass is already there. In some cases, researchers use an unused fiber inside an existing telecom cable. The cable route may already run beside roads, railways, pipelines, or across the seafloor. That creates a ready-made line through places that are hard to monitor. And earthquakes are only one kind of shake. The same idea can detect passing trains, traffic, construction, ocean waves, and sometimes changes around underground systems. But a cable is not magic. It only senses motion that reaches the cable. A loose cable may respond differently from one buried firmly in the ground. And it does not instantly explain what caused every vibration. A truck, a storm, and an earthquake can all make patterns. Scientists compare the timing, strength, and shape of those patterns. They also compare signals from other sensors. That helps them separate a local rumble from a real earthquake wave. The biggest advantage is coverage. A normal earthquake sensor measures one location. A fiber can measure a long line of locations, meter by meter. That could fill gaps where ordinary sensors are rare, especially along coastlines and beneath the ocean. Imagine an undersea internet cable crossing hundreds of kilometers of seafloor. It was built to carry videos, messages, and game data. But when the seabed trembles, the same glass strand can reveal where the shaking traveled. The cable never hears sound like a person does. It notices its own shape changing. And because light can detect that change so precisely, an ordinary internet cable can become a giant earthquake sensor.